I'm going to look at the first part of bonding in this video. So we will look at ionic and metallic bonding first. Before we totally jump into this, we just want to make sure that we understand what a bond is. So a bond is anything that holds atoms together. So it's some form of mutual attraction that holds atoms together. And there are three types: ionic, metallic, and covalent. And we will go through all three, but you can see them here in picture form. An ionic bond is when you have a transfer of electrons. A covalent bond is when you have a sharing of electrons. And a metallic bond here in the center is when you have these free floating valence electrons, which we will look at. So it's all about the differences in electronegativity, which determine the bond type. So if you remember, electronegativity is an element's ability to attract electrons toward itself. So depending on whether a particular element wants electrons or doesn't want electrons is going to determine the type of bond that forms. So ionic bonds here, when you have a transfer of electrons between atoms, literally one element in the bond doesn't want the electrons and the other element wants them. So there's a transfer taking place. If you look at this picture here with sodium and chlorine, you can see sodium would have one valence electron that he wants to get rid of. He's a metal, he's going to form a plus charge, and chlorine has seven valence electrons, so he wants one valence electron. So literally, sodium sends that valence electron to chlorine. Sodium becomes positive because he lost an electron. Chlorine becomes minus because he gained an electron. And that opposite charge, those opposite charges that form, bring those two atoms together and make them stuck like glue. Okay, an ionic bond is the strongest of the bonds we're going to look at. So remember, ionic bonds, transfer of electrons between a metal and a nonmetal. All right, and then a formula unit is just when you write the overall formula for an ionic compound. It's basically the lowest whole number ratio for the metal and the nonmetal that make each of them happy. So there is actually a way to show this ionic bond forming when one element transfers electrons to another. So I'm going to walk you through that in a minute, but the steps are here if you want to pause and look at them. But I think it's easier when I actually show you a couple examples here for you to get a good idea. But the basic gist is you would just show the electrons transferring using arrows, and then you make sure you pay attention to the charge on each, and you write the overall formula unit. And this has to continue until every element in your ionic bond is essentially happy and has the number of valence electrons that they want. Okay, so as I said, it's easier to do these just jumping right in and doing examples. So we want to show the ionic bond that would take place here for sodium and chlorine. And we're going to show the transfer. I'm going to show you everything you need here to get these right. So the first thing you do is you write the dot structure for each element. So we've done dot structures already earlier in the course. So we'll start with sodium. All right, so the dot structure for sodium, you'd put the symbol for sodium, so Na, and you look up on the periodic table how many valence electrons does sodium have. He's in the 1A column, so sodium has one valence electron. All right, do the same thing for chlorine. Chlorine is Cl. All right, so chlorine is in the 7A column. Chlorine has seven valence electrons. So remember, one on each side until you're forced to pair up. So if he has seven, there's going to be one side that just has one. All right, it doesn't matter which side. All right, so then you always look at this and say, okay, who wants to lose? Who wants to gain? All right, so just remember here, metals always want to lose. All right, and non-metals want to gain. So in this case, the sodium wants to lose his electron and chlorine wants to gain. All right, so you use the arrow to show the transfer, show the ionic bond. So this electron from sodium will go to an empty space there on the chlorine. All right, but when this happens, sodium has now lost one electron. All right, that's losing a 1 minus. All right, every electron is 1 minus. So sodium now becomes 1 plus. All right, and you have to show that because that indicates that he is happy essentially. He has that noble gas configuration that he wants. But on the other hand, chlorine has gained one electron, so now chlorine is 1 minus. You have to show those charges to indicate that the transfer took place. All right, when this takes place though, everybody in this picture is now happy. Sodium has lost the electron that he wanted to lose. Chlorine gained the electron that he wanted to gain. So everybody in this picture is good. So the last thing you would do is you'd write the formula unit for the compound that forms. So you always write the metal first, sodium, Na, and then you count in your picture how many sodiums were needed. All right, we only drew one, so it's just one sodium, but you don't put the one. And then you say, okay, the non-metal goes second, chlorine. How many chlorines did you have? There's just one, so you don't put the number. So the formula unit for this compound would be NaCl. It takes one Na, one Cl in order to make the transfer take place and each element in this ionic bond to be happy or have that noble gas configuration. So this one was pretty easy. So now we're going to try another example here, one that's a little bit more fun. So we're going to do the same thing, but we're going to do calcium and phosphorus. All right, but the same steps here you need to follow. So the first thing you do is you draw the dot structure for each element. So I'll start with calcium. All right, so calcium is Ca, and it's in the 2A column, so it has two valence electrons. One, two. All right, and then we have phosphorus. Phosphorus here is in the 5A, so he's got five valence electrons. All right, remember, it's going to have one on each side before it's forced to pair, so it will just have one side that has two. All right, and now the transfer is going to take place. The metal always loses, the non-metal always gains. But in this example, calcium needs to get rid of two. All right, and phosphorus wants to accept three because phosphorus just has five, so he wants three more in order to get eight. So calcium will send his valence electrons to an empty space on the phosphorus. All right, so at this point, when you transfer those two electrons from the calcium to the phosphorus, calcium has lost both of the electrons that he wanted to. So he lost two electrons, calcium is happy, and calcium now has a 2+ charge, and you must show that, okay, because calcium lost two electrons. But right now, phosphorus is not happy. Phosphorus is still missing one of the electrons that he needs here in order to get that noble gas configuration. He wants one more. But at this point, this calcium here is tapped out. Okay, he has no more electrons to give. So the only way we can make phosphorus happy is if there is another calcium. All right, so remember, if this was taking place, there would potentially be millions of these atoms available, so another calcium just comes in. But every calcium comes in with two valence electrons. Even though phosphorus needs one more, every calcium comes in with two. Okay, so calcium will send one of his electrons to the empty space there on the phosphorus. At this point, phosphorus has now gained three electrons. Look at the picture. There are three electrons going to the phosphorus. He is now happy and he has a 3- charge. Remember, you can confirm this on the periodic table. Phosphorus is in the 3- column. He would want to gain three electrons. All right, but if you notice, you can't stop here because now you have a calcium that is not happy. Okay, this calcium here at the bottom has another valence electron that he needs to get rid of. All right, he can only send it to a phosphorus, but that phosphorus is now done. So another phosphorus would come in, right? But every phosphorus would come in with five valence electrons. All right, so calcium now says, okay, I can send a valence electron to an empty space on the phosphorus. At this point, calcium has lost two, so he's 2+. All right, phosphorus, though, has only gained one. So phosphorus is not happy. All right, phosphorus needs two more valence electrons. The only place he can get is from a calcium. So another calcium has to come in, but each calcium comes in with two valence electrons. So one can go here, one can go there. At this point, calcium lost two, so it's 2+. Phosphorus has gained three, so 3-. At this point, every element in your picture is happy. Okay, there's a charge listed for all the elements. They have reached their noble gas configuration. You are done. All right, so now you're ready to write the formula unit. So you write the metal first, Ca, and they say, okay, how many Cas were needed in order to complete this ionic bond? Well, in your picture, there are three calciums. Okay, so there's three calciums, and then you write the nonmetal, phosphorus. How many did you need? You only needed two. Okay, it's essentially symbols, charges, crisscross, but you just count the numbers that you needed in the picture here. So that would be the formula unit. This is what you would need to show in order to get full credit for one of these problems. Just an FYI, this is the longest one of these problems could go as well. 3 on one side, 2 on the other. All right, so if you start getting into this and you start needing more and more and more elements, then you know you probably missed something and did it wrong. So we can try one more example here. If you want to pause the video and try it on your own, that's fine. but I'm going to jump right in here and solve it. So we're going to do this for magnesium and chlorine. All right, so same deal. Magnesium, all right, has 2 valence electrons. All right, he's in the 2A column. And then chlorine has 7 valence electrons. All right, so you're going to have one side of the chlorine with just one. All right, magnesium is the metal. He's going to send his electrons to chlorine. But once magnesium sends one electron to the chlorine, chlorine is now done, essentially. He has that magic number of 8. So chlorine is a 1 minus charge. All right, magnesium, though, is still not happy. He needs to get rid of one more valence electron. He can only send it to a chlorine. So another chlorine comes in, but each chlorine comes in with 7 valence electrons. So then magnesium will send his other valence electron there to the chlorine. Chlorine becomes 1 minus. Magnesium lost 2 electrons, becomes 2 plus. Every element in your picture has a charge. Everybody is happy. So now you write the formula unit. Metal's written first. There's just one magnesium in your picture, so it's Mg. Then the nonmetal, and there were 2. So the formula unit here for this compound would be MgCl2. All right, you need 2 chlorine for every 1 magnesium in order to complete the ionic bond, to complete the transfer of electrons. So I'm just going to walk you through some basics here for ionic compounds and some of the properties. You're more than welcome to pause the video. I might go through this pretty fast, but we already know that ionic compounds are made of metals and nonmetals here. All ionic compounds are known as salts. You're used to hearing table salt just referred to as salt, but all ionic compounds are salts. And basically what happens is you take those formula units and they just repeat over and over again, and they form these nice beautifully arranged structures. Okay, so ionic compounds are very organized, very arranged. The first property of ionic compounds here are that they are very strongly bonded. Okay, think about this. Metal, non-metal, metals become positive, non-metals become minus, opposites attract. They form a really, really strong attraction here between the two ions. Okay, because they have a very strong attraction, they form these very organized structures, which we call a solid crystal lattice structure. Okay, they are beautifully arranged, regular repeating pattern, and oftentimes they do form crystals. If you look very closely at some table salt, you will see those crystals. Okay, so very organized, very stable structures for ionic compounds. Because ionic compounds have that very strong attraction between the opposite charges, they have very high melting and boiling points. Okay, the opposites are so strongly attracted to each other that these things don't really want to come apart. So you need a lot of energy here to make them melt or boil. If you look over here, all right, this is just magnesium chloride. Melting point is over 700 degrees Celsius. Boiling point is over 1400 degrees Celsius. So very high melting and boiling points. And then something interesting here, ionic compounds are typically soluble in water, so they will dissolve. But something else happens as well, okay? Not only do they dissolve, but they actually do something interesting called dissociation, okay? So when you put an ionic compound in water, they don't just dissolve, they actually separate into their ions. So if you were to take table salt, sodium chloride, and put it in water, all right, it doesn't just disappear, it actually separates into Na plus ions and Cl minus ions. And you might say, well, why does this happen? Because, you know, sodium and chlorine, they both have those opposite charges. They should want to be, stuck together like glue. Well, what happens is here, as you'll find out, water has these regions of charge. So when the Na plus comes apart from the Cl minus, the water turns and points its negative regions toward the Na plus. So he essentially becomes surrounded by negatives, so he's thrilled. And then the opposite thing happens here for chlorine. When chlorine comes apart, he's minus, so water turns and points all the positive regions of the water toward the chlorine, so he becomes very happy because he's surrounded by positives. All right, so as long as the water is present, these ions stay apart. But then when the water disappears and evaporates, the Na plus and the Cl minus will come back together, and that's when, if you see like water evaporating, you see the salt reforming, okay? So very important, ionic compounds don't just dissolve in water, they actually dissociate or literally separate into their ions. Okay, this is very important for future learning in chemistry. Another property here of ionic compounds is that they will conduct electricity, but they will only do this when they are melted or dissolved. Okay, we just talked about how when you put ionic compounds in water, they literally dissociate into their ions, into the pluses and the minuses. All right. In order to be able to conduct, you need negative charge to be able to flow. When an ionic compound is together here in the solid form, it's too orderly. Okay. The plus and the minus are stuck together, so the negative cannot flow. It cannot conduct electricity. But as soon as you melt it or put it in water, those plus and minus come apart, and this allows the negative charge to be able to flow and allows the electricity to be conducted. So very important to remember that ionic will only conduct when melted or dissolved. So the last major property of ionic compounds here is that they are extremely brittle. All right, if you hit them hard enough, they're just going to shatter into a million pieces. And if you look at your container of table salt, you will see this. All right, the little grains of salt are already in pieces. And the basic gist is that these ionic compounds have these very organized, very stable structures where the plus is, attracted to the minus and everything's perfectly aligned. So if you hit that um, compound hard enough, you essentially form light charges to come in contact with each other, which would just cause the entire structure to kind of break apart, repel, and shatter here. Okay, so ionic compounds are very brittle because of this. All right, so as I said, we were also going to talk about metallic bonds in this video. Metallic bonds are not really bonds at all. These are just the attractions that allow metals to kind of be on their own. Okay, people always confuse metallic bonds because they think, oh, it's a metal bonded to another metal, but no, that doesn't happen. It's not like a diatomic or anything like that. It's literally just the metal itself. Okay, so what happens here is metals don't want their valence electrons, they actually want to get rid of them. So what happens in a metallic bond is that we say that there are these free floating valence electrons. Okay, so you kind of like each metal atom dumps its valence electrons and they're shared between all the different atoms. Okay, so it's easiest, think about if this was a piece of aluminum foil. It would just be aluminum, all right, but there would be multiple atoms of aluminum. So what happens here is all the nuclei of the metal want to get rid of their valence electrons. So they all kind of dump the valence electrons out here, and the valence electrons are just free to move between all the different positively charged nuclei of the aluminum. Okay, so it's just aluminum. Okay, but this is what allows a metal to exist by itself. Okay, because think about it, this metal is looking for a nonmetal. It would like to send its electrons to a nonmetal so you can form that ionic bond, but it's not available. All right, so they literally here, each atom just dumps its valence electrons, and those electrons are free to move between all the different metal atoms. Okay, so these are not ionic, all right, but they do have a lot of similar properties to ionic. And we say that these positive cations here, these positive nuclei, are floating in what we call a sea of electrons. It's not a real sea. Okay, every year I get somebody telling me that the electrons are going swimming or something like that. It's not really that. But this is what keeps metals stable and allows them to exist by themselves. They're not actually bonding to anything, despite what the name is. So basically, in a metal or in a metallic bond, all right, all these valence electrons are free to move between all the different metal atoms. Okay, so being able to move here, all right, is what leads to what we call this sea of electrons. All right, free floating valence electrons in a metallic bond. So we already know a lot of the properties of metals from previous units, but basically the reason why these properties occur is because of these free-floating valence electrons, these valence electrons that are mobile. Think about it, all right? Metals are malleable and ductile because if you hit them, all right, the valence electrons are free to move, so they would just rearrange themselves to prevent any repelling. So metals bend, they don't shatter like an ionic compound. They literally just rearrange the electrons, prevent repulsions from taking place, which allows the metal itself to be bendable rather than shattering here. But they're also conductive for this reason as well. Metals are conductive in their solid form because the electrons are free to move. They don't have to be dissolved like ionic compounds. In a solid form, a metal will conduct because those valence electrons are mobile, because they have these free floating valence electrons. So this is great because it shows you the difference between ionic and metallic here. So notice here on the left, all right, if you hit a metal, all right, because of those free floating valence electrons, they just move around, reposition themselves, and prevent the positives from repelling each other, and it allows the metal to bend rather than break. But in ionic compounds, they are so organized that if you hit them, all right, you cause like charges to come in contact with each other, and this causes a repulsion, which causes the shattering and causes ionic compounds here to be brittle. So the free-floating valence electrons in a metal allow it to kind of slide like grease, and it makes the metals bendable. The last thing we're going to talk about here are alloys. Alloys are mixtures, all right? So if you think back to what mixtures are, but they're mixtures here in which one of the substances is a metal. Okay, so we might have mentioned these earlier on, but didn't call them alloys. But the basic gist is usually you mix these things, you heat them up, cool them down, and you get these alloys forming. So there's some examples there. Brass is a mixture of copper and zinc. Bronze is copper and tin, and steel is usually iron with some other things mixed in. All right, so these exist and they are created all the time here in industry for various reasons, as we're going to see. You might be thinking to yourself, well, why would I want to make an alloy? All right, what's the purpose? Why don't I just use the metal itself? Well, we get properties here that are superior to the individual elements. All right. So copper is great, but it might have some downsides to it. All right. So you can mix in another metal and then you get a better material. So some other examples here. Sterling silver is mostly silver, but it has a little copper mixed in. All right. It's harder. It's a little bit more durable than pure silver. Silver is pretty soft. All right. So it would perhaps break in jewelry, but if you mix in a little copper, make sterling silver, makes it a little bit harder, but still easy enough to work with, so it would make your jewelry last a little bit longer. Steel, much better than using iron, okay? It's corrosion resistant, but it's still hard, it's very cost effective, all right? So we make these alloys here because they give us better substances, all right? A lot of companies out there will make their own alloys for different things. Apple has made some aluminum alloys for their phones, all right, and usually they get better properties here than the original element itself.